Hi guys, it's Dr. Orlando. I'm going to do a quick video on covalent bonds. We talked about 3 different types of bonds in class: covalent bonds, ionic bonds, and hydrogen bonds. So this is the first one of those. So we're talking about binding stuff together. So in fact, what does bind together in a covalent bond? You're looking at binding atoms. So it could be 2 of the same kind of atom. It could be 2 different atoms. Okay, so we're binding atoms together. How are we binding atoms together? We are sharing pairs, underlined pairs, of electrons. Okay, because they're always shared in pairs here. How many bonds can we make? How many pairs can we share? Well, we are interested in sharing up to 3 pairs. So if we share 1 pair is shared, then you're looking at what we call the single covalent bond. Okay, and some examples. I've drawn this a zillion times in class. As I draw it, your brain should be saying what this molecular structure is. Hopefully you came up with methane, and you notice that you've got a carbon surrounded on all sides equally by, let me fix that. I don't want those to look like double bonds. That would be bad. Okay, try again. There we go. That's better. Sorry about that. So there's methane with single covalent bonds between each of the hydrogens. So you would say that there are 4 single covalent bonds here. Okay, and between each hydrogen and the carbon, that line right there, that line, single dashed line, represents the sharing of 1 pair of electrons. Okay. All right, so that's what we call the single covalent bond. So now what if we share 2 pairs? Are shared. 2 pairs of electrons are shared. Okay, so we could take something like this. Again, I hope as I draw this, you are, in your mind, coming up with what that is. You see a carbon and 2 oxygens. This is carbon dioxide. Okay, and you can see these double dashed line here. That indicates that we are sharing 2 pairs are shared. When I say 2 pairs, it's 2 pairs of electrons. So we call this the double covalent bond. Okay, double covalent. All right, go to our next page. Still working on covalent bonds. Okay, so we did 1 pair shared, 2 pairs shared. We can share 3 pairs shared. Again, we're sharing 3 pairs of electrons. So if we're sharing 3 pairs of electrons, that's 6 total electrons that are involved in the sharing. And you might see something like this. Let's get a color here. Carbon triple bonded to another carbon. Now you know carbon likes to make 4 bonds, so it must bind to something else, and a nice thing to bind it to is always hydrogen. So this is acetylene. And you can see those right there. That indicates that those 2 carbons are sharing 3 pairs of electrons shared, and that's what we call the triple bond. Now there are covalent bonds that can share up to 6 pairs of electrons so far that have been discovered, and maybe more. But as far as I have read, 6 is the most that they've ever shared. We are not interested in any of those for biological purposes. Pretty much single, double, and triple covalent bonds will cover us. So then you have to ask yourself about the sharing. Is it equal? Is it equal sharing of the electron pair? Okay, so does one of the atoms get to have those electrons more than the other atom, or are they sharing them equally? Okay, so they are divided into 2 categories here. Let's put that line there. Okay, I'm going to make like a little chart here. So we have the polar covalent bond and the non-polar, it's an A there, covalent bond. Okay. Polar and non-polar covalent bonds. Okay, so with the polar covalent bond, when you think of the word polar, think of the poles of the Earth, the North and South Pole, that they have opposite ends, and so does a polar covalent bond. It has opposite ends. It's not hot and cold or anything like that, but it is positive and negative. So a very easy one to remember and draw, and a very important one is water. We're going to talk about water when we talk about all the different kinds of bonds, because it does play a role in each of them. Okay, so there's water, and you can see that water has 2 single covalent bonds. It has a bond between the oxygen and the hydrogen, and it has here, single, and it has another one between this oxygen and this hydrogen. Okay, so that's our water molecule with our 2 single covalent bonds. And the reason that it is polar is because we know that water has a slightly negative side and a slightly positive side. How do we know that? Well, we are able to, not me personally, but scientists are able to analyze and figure out where those electrons spend their time. And in fact, the electrons like to hang out more with the oxygen. They spend more of their time around the oxygen molecule. The electrons are more attracted to the nucleus of the oxygen than they are attracted to the nucleus of the hydrogen. Kind of makes sense. The oxygen's nucleus is bigger, has more protons, so the electrons want to hang out more around the oxygen. So the electrons are negative, so that makes the oxygen side of the water molecule more negative. Okay? And it makes the hydrogens more positive because the electrons aren't there. The negative is not there, so they become more positive. So water has this negative and positive ends, and a lot of times you will see it drawn. I'm going to erase this so I can draw it again. You'll see that, those Greek symbols in there. Let's see if I can draw it a little bit neater. Got the oxygen, the hydrogen, hydrogen. Okay. And then the charges, I'm going to draw in green. Again, the oxygen has that negative charge, and it's not a full negative charge. It's not a -1 charge. It is a partial negative charge. So you draw this little guy here. It's the Greek letter delta. Okay, and you put a little negative to it, and that actually means partial negative charge. Okay, whereas down here, we're going to draw a little delta positive. Delta positive. The hydrogens have a partial positive charge. Okay. So when you see those delta negative and delta positive, it tells you that it's a partial charge, not a full -1, -2, whatever. It's partial. Okay, so it's slightly negative, slightly positive. Kind of looks like an S, so you can think of it as slightly. Okay. All right, so that's our polar covalent bonds. Now our nonpolar covalent bonds, with the nonpolar covalent bonds, you want to look at something like this guy, which I've drawn before. Again, I hope when I draw him, you go, aha, that is methane. And with methane, these bonds between the carbon and the hydrogen, these single covalent bonds, these have equal pulling strength. So these hydrogens are pulling on that carbon in the same amount of strength that the carbon is pulling on the electrons. Okay, so those are equal sharing. There's no charge here. If we were to actually tag one of those electrons and follow it around and measure the amount of time that it spends at any one place, you would find 50% of the time it's around the carbon and 50% of the time it's around the hydrogen, pairs of electrons. Okay? We would see that they spend equal amounts of time there. So we say this is nonpolar. You don't see any charges. Very often when you see these drawn, to give you a little clue, you'll notice that this is drawn very symmetrically. Okay? Whereas water is drawn bent. Yeah, it's bent. The little hydrogens are at the bottom and the oxygen is at the top. So that you could just as easily, you could draw water like this, right? It wouldn't be technically wrong at all, but it wouldn't show the polar nature of it. So I don't like to draw it like that. I like to draw them bent, so to remind you guys that it's not symmetrical, and it is polar. All right, there you go. If you have any questions, please feel free to call me or email me.